Okay, so in this video I'm going to show you guys how to make some graphs in MATLAB for the data that you have from Excel. I'm going to use the data from the first lab, stress and strain, and a lot of this though you can use in the other labs in the semester. So let's go to Excel. As you see, I have aluminum, blue steel, and red steel. I have all the data here. And the data that you had were in these 4 columns. You had the load, the time, the crosshead position, and the deformation. The time, the crosshead, is not important for this lab, so you can disregard that. Now I've made these 2 columns here for the aluminum stress and the aluminum strain. To do this, all we do is click in this box, and you're going to type equals, and then you're going to click on the load here on the left, and then you're going to divide that by your cross-sectional area, which is constant. Okay, we keep our area constant in the calculation. So to do that, we have these dollar signs. Okay, and then once you do that in this box, you're just going to click and drag down after you press enter. And once you do that, let's go to like row 15. Then you see I have this new load value, but the area is still constant. So we're going to do the same thing for strain. Our deformation, delta L, that's going to change, but the original length of 2 inches, that's constant. And then we're going to see the difference. Once again, we have a new delta L, but the original length is constant at 2 inches. Okay, so do that for aluminum, blue steel, and red steel. Okay, let's go into MATLAB now. You're going to save your file, of course. Then you go into MATLAB, and we're going to go to New Script. This is where we're going to write the code to make our graphs. The first thing I'm going to do is percent define knowns, and when you do a percent in MATLAB, that's telling MATLAB to disregard anything after that percent sign on that line. So it's a good way to write comments that will help you out to stay organized and to sort out what your code is doing for each line. So I'd recommend doing that. Okay, we're gonna go to Save As. Save it in a document or in a folder that you want. Okay. Call this Lab 1, and I'll just say Video 2. Okay. So now it's saved. Now we're going to import the data, so on your tabs up here, go to Home, Import Data. Okay, we're going to find the data that we want to import. And here we go. Now a window is going to pop up. And this is showing all of the Excel data that we just had. So I have aluminum, blue steel, and red steel. All we care about is the stress and the strain. So we're going to get these 2 columns. Now I'm going to go down and I'm going to take out this last value here for the stress and strain. I don't care about that because there's a huge drop off. At this point right here, at where my cursor is, we've already fractured the specimen. So I'm going to take out the last point. Now I'm going to go up here and I'm going to call this aluminum stress and then aluminum strain. And then where it says output type, make sure that's a column vector. If it's a table, you're not going to be able to plot your stuff easily. So make it a column vector. Click on Import Selection. And now if we go to MATLAB, now I have the aluminum strain and the aluminum stress. Okay, we're going to do the same thing for the blue steel and the red steel. So get these two columns, take out the last data point, make sure it's the last one, so scroll down all the way, and then blue stress, blue strain. I don't need that column. Okay, import red steel, scroll down, take out the last one, red stress, red strain, and import. Let's check it's all there. It's all there. Now I'm going to go back to this home tab and save the workspace. Put it in the same folder. Lab 1, video 2, and save it. So it's going to save this workspace that we have. Make sure you save it, because if you don't and you open up this script again, none of this is going to be there and you're going to have to re-import all of this data. Okay, so I have this line right here for define knowns, but it's actually not necessary to do what I did in class, like this. Yeah, it's entirely unnecessary. I didn't really think it through in class, so they're already defined. They're just defined in our workspace right here. So we don't need to type them out here. We can still call on these column vectors from the workspace into our script. Okay, basically, these names here, these are the variables that we have basically assigned in the workspace. So, I'm just going to take this out. So, let's do graphs. Okay, so just like in class, I'm going to graph all three of the specimens on one graph. So I'm going to title this All Specimens, Entire Range. And let's start off with aluminum. So I'm going to do plot, alum strain, comma, alum stress. And then I'm going to do this in green. And then we'll do the line width of 1. Now if I run this, I get the graph. So remember, we want the aluminum strain on the horizontal axis and then the stress on the vertical axis. Okay, now we're going to do, or let me go over this really quick. So I plotted my X and my Y. The G stands for green, so we have a green line. And line width of 1, that makes our graph, the curve thicker than the default value. So if I take this out, just like this, and I run it, I think that is it. Okay, so yeah, the line here, the curve isn't as thick. So if I put line width back in here, and we run that, now we have a thicker line. It's easier to see. And remember, this is going to be part of the clarity on your syllabus. I want to be able to see what's on the graph easily. Okay, to graph the other two, we're going to do hold on, so I can plot the other data on the same graph. So plot blue stress, comma, blue strain, comma, blue stress. And we'll do this in blue. Line width of 1, plot red strain, red stress, red, line width of 1. Okay, let's take out that comma, and then hold off. Need a comma right there. Okay. And let's run that, and now I have all three graphs on the same plot. Okay, now we're going to do our labels. So we'll do a title here. All specimens, entire range. Okay, there we go. So that's our title. Got it right there. Let's do X label. Spell it correctly. X label, strain, inches per inch. Y label, stress, pound force, per inches squared. Okay. We all good here? Nope. You see, there's this red line. It's telling me I did something wrong in this line of code. I forgot the little quote. Apostrophe. Yeah. Okay. Run it. And here's our figure with the labels. Like I said in class, I want the inch per inch and pound force per inches squared. I want that as a nice vertical fraction, so to say. So I'm going to modify these lines of code. So I'm going to write strain. Let me go to my notes really quick. Okay, so I'm going to do strain, $, display style, frac, two curly brackets, $, apostrophe, interpreter, and then latex, or LaTeX, depending on how you want to pronounce it. Okay. Now let's delete this. Then inside the curly brackets, we're going to put inches per inch. The first curly bracket, that's the numerator of our fraction. And the second one, that's the denominator of the fraction. So in this code right here that's highlighted, we're telling MATLAB to reference this code as LaTeX code. So display style, that's saying, okay, display this in math mode. And then fraction, or frac, that's saying, hey, I have a fraction here, and then you specify the numerator and the denominator. Let's copy this code. And let's put it in here, and I'm going to change this to pound force underscore F, then per inches squared. The underscore, that denotes a subscript. I want the F for pound force as a subscript. So let's run it. And then I get inches per inch and pound force per inches squared. Maybe I want some parentheses around the inch per inch and the pound force per inches squared. So I'm going to do parentheses here. Let's see how it looks. Okay, so I have parentheses, but it's not the entire vertical height of this fraction. So we can fix that. I'm going to type in left. It should be, okay, let's retype it left, and then the left parentheses, and then right, and then the right parentheses. And now we have parentheses on that whole vertical fraction. Let's do it for this as well. Okay, so left, and then we need this backslash before the fraction. Make sure that's there. And then right. And now that looks quite nice. Okay, let's go back to the graph. So I have an exponent on my vertical axis, and you also might have one on your horizontal axis. So let's get rid of those. Fixing axes labels. Okay. We're going to type in for the x-axis, ax equals the GCA, ax.xruler, make sure the R is capitalized, dot exponent with the E capitalized equals 0. Then AY equals GCA AY dot Y ruler dot exponent equals 0. Okay, so then we can run that. And if we run it, now we have whole numbers for the vertical axis. So we have 20,000, 40,000, etc. Pounds per square inch. Okay. Now I'm going to make a graph for blue steel in the elastic range. Okay. So for this, I'm going to plot blue strain, comma blue stress, and we'll make it blue, line width of 1. Now I'm going to go back up here, and here I'm going to call this figure 1. Let's first run it like this. So you see, I only have the graph right now for what I just plotted. I'm not getting this graph up here. So if I do figure 1 for the first one, and then for this one, figure 2, and I run them, now I have both graphs. So name each figure with some number, and then you let MATLAB know that you have more than one figure. Okay, now let's make this for the elastic range, because right now, this is for the entire range. I'm going to go to blue strain, 1 to 318, blue stress, 1 to 318, comma 1, run it. Now I have a graph that goes past the elastic range here. But I'm doing this because we're going to use that offset method. So I'm first going to copy and paste all this. Let's paste it down here. Let's change the title. Blue steel, elastic range. Maybe you want a different title like yield stress, or I don't know, something like that, because technically we're going past the elastic range. Up to you. And then, okay, let's run it. So, for defining the yield stress, I don't really see the exact point when this is no longer linear. So I'm going to use the offset method to define a yield stress. So we need to start at 0.002 inches per inch, or 0.2%, and we're going to draw a line that's parallel to the elastic range right here. When we draw that line parallel, we're going to have an intersection point somewhere in this yielding region, and that's going to be defined as the yield stress. So to draw this line, I need to know the slope of the elastic range. To do that, I'm going to take 2 points, right, just rise over run, but I want to have a range of values so I can minimize the error. So I'm going to take a sigma 2 minus sigma 1 all over epsilon 2 minus epsilon 1. So let's go back into Excel, or let's go here really quick. So I want some region where it's linear. So for this video, I'm going to choose the points from 0.1% to 0.2% strain. So let's go to Excel for blue steel, and I've already marked some points in here. Here's 0.1 at 0.1%, and here's 0.2 at 0.2%. So this is sigma 2, and this is epsilon 2. This is sigma 1 and epsilon 1. So I've calculated the elastic modulus for the blue specimen right here. That equals sigma 2 minus sigma 1 all over epsilon 2 minus epsilon 1. And that gives us our elastic modulus, which is also the slope in the elastic range. So we can go ahead and copy that let's go right here, and I'm gonna make a comment for plot offset line. I'll do x underscore o, or x off, equals 0.02, 0.001 to 0.006. Now this is saying that I want to have a graph starting at 0.2%, going to 0.6%, and that's going to be our domain, our x domain. And this middle number here, that's the step counter for our data points, so basically how smooth that line is going to be. Let's define our y data now. I'll do y off equals our slope that I just copied and pasted, x minus 0.002. Now let's plot x off, y off. Okay, before we do that though, see, this is one figure all right here. I plotted two things, so I need to do hold on, then I'll do hold off. Let's run it. Okay, I have an error. What did I do? Okay, I forgot to multiply it right here, so I need to include this symbol to multiply. We have another error, line 32. Okay, yeah, this needs to be x off. Okay, run it now. Now we got it. Okay. So I've made this line that's parallel to our elastic region, and I've started it at 0.002. This part right here in our equation, that's saying to shift over from the origin and start at 0.2% for the offset. And that allows us to get a graph like this. Okay, so now I want to find this intersection point, and that's going to be the yield strength. So we gotta have some more code. Let me clear that. Okay. Use another comment. Find intersection point for yield strength. Okay, we're going to use brackets xi comma yi equals, poly x, poly y, and then we're going to do it for blue strain from 1 to 318, comma 1, blue stress 1 to 318, comma 1, comma x, comma y. Now we're going to run this. Okay. This needs to be off. Sorry, before I just used x and y, so I keep forgetting that. Okay, so x off, y off. Now I get xi and yi. That's the intersection point right here. Okay, so yi, that's basically the yield strength, because that's on the vertical axis. That's going to be this number right there. That's going to be the yield strength. Okay, so you can just write that down in your report, because you need to record that data. Now I'm going to comment out the plot for the offset line. We don't need that anymore. Let's clear this again. I'm just distracted by the error. Okay, now I'm going to go under my label section, and I'm going to label the yield strength. Okay, so I need to do plot xi comma yi, because that's the intersection point, and we'll make this a black star. So k is black, and the star. Now when we run that, Okay, again, I have hold off here, so I need to go here and then say hold off, so I include all the graphs. There we go. Now I have that intersection point right there. Now let's get a text label for that intersection point. I'm going to do text 0.005, comma 110,000. Then I'm going to label this yield strength. Let's run it. And I got yield strength right there. Remember, you can do insert text box. Then you have the box. There might be a way to remove the box, because to me, that does not look as nice as the label that I just made. Okay. It's not letting me type. Let's try that again. Insert text box. Yield strength. Obviously make that an appropriate sized box, but this does not look as nice to me as this. Okay. So if we look at this graph here, we need to find the region for the elastic range. Now, because it's kind of hard to tell when it stops being linear, you're just going to have to kind of eyeball it. So to me, this seems like it stops being linear around 0.3%. In your report, you should spend more time than I'm going to do in this lab or this video. But I'm going to differentiate the elastic range from when it starts yielding by using a different color for the curve up to that point. So let's go here. I'm going to plot a whole new thing, and I need to now move hold on right there. Plot blue strain. I'm just going to guess right now like 230. Blue stress 1 to 230. And we'll make this, I think that's pink. Okay, we good. And let's run that. I need to change this. We're gonna do 230. 230. Okay, so that gave us a marker. So let's change this to red. Okay, there we go. So now I'm showing the elastic range here. It probably continues a little more to like here. But for the sake of the video, let's pretend this is the elastic range. So I'm going to add some text for the elastic region. So I'm going to do text 0.002, and we'll do 45,000. And we'll say elastic region. Let's run it. So then I get this text right here. So I chose 0.2% for the strain, so it starts right here, and then 45,000 for the stress basically, and that's going to place our text right here. So I can move it, a little closer and whatnot. But let's say I want to have this text in red. So let's go back here. I'm going to do comma, color, comma, square bracket 100. Okay, and that should give us red text. And there we go. So now it kind of matches a little more. We can do the same with yield strength. Let's try that. Color. And we'll do 0, 1, 1. Let's run it. So this gives us cyan. We can make it blue if we want. Let's make it blue really quick. Blue is 001. Okay. So I think if you are changing the text color, you need to use this format where it's 3 numbers, zeros or ones. That's what MATLAB wants. And I'll leave a little link to a website that I'm using to reference these numbers for each color. Okay, so for this graph, we have aluminum in green, blue steel in blue, and red steel in red. That's fine, but really we should show on our figure here a legend. So let's add that in right now so someone that doesn't just know that green is aluminum and red is red steel and blue is blue steel, they'll be able to know just from the graph. Okay, so I'm in my figure for all specimens. I'm going to go under labels here and I'm going to type in legend, aluminum, blue steel, and then red steel. Okay, so that's taking aluminum, blue, and red in order like that. Let's run it. And now I have a legend that's showing that green is indeed aluminum, blue is blue steel, and red is red steel. Okay, so now I'm going to save the graphs that we made. Let's run the script. Okay, let's take this file. We're going to go to File, Save As, put it in a Graphs folder, and I want to save it as a scalable vector graphic, or .svg. And I'll explain why once we go to Microsoft Word. So, blue steel elastic. Okay. All specimens. Entire range. Okay. Let's go to Word. I want to insert pictures, graphs. Let's open both of them up. Alright, so now I have a high quality image here. Let's crop it just to demonstrate something. I'm going to crop it like this. Okay. Here we go. Now I'm going to use Shift. Let me delete this. I'm going to click on here. I'm going to hold down Shift and drag it out so that aspect ratio is maintained. And you see when I rescale it, I still have really good detail here. Nothing has been lost because I saved it as a vector. If you save it as that scalable vector graphic, I think it was, you're going to be able to preserve all this really nice detail. Now if we instead, just for comparison, let's save this as a JPEG. That's what a lot of people do, right? We'll do, and that was the blue steel. Elastic. Let's go here. Delete that. Insert picture. Let's open them up. Alright, oh boy. See, I don't even know exactly which one went where, but I can tell just by looking at it, this one is the JPEG, and this is the scalable vector graphic. Let's crop in on this one. Picture format, okay, let's crop. Again, I'm going to go like this, crop it, same for here. And now you see it says graphics format. Let's crop that in as well. Crop it. Okay, redo it. I messed up. Okay, now crop. Let me just move this in front. Okay, there we go. So look, I can tell this is the JPEG. There's a lot of artifacting going on. If I make this bigger now, you can see all of these artifacts, especially along the red line here. It looks terrible. If I go here and I make this bigger, Let's move this out of the way. You can see all that detail is still really nice and clean. So use the SVG file format and your graphs are going to look amazing. Okay, so I think that's all I'm going to cover for this video. If I forgot something or you have a question, email me or go to office hours, you guys know. But I hope this helped you out, and hopefully it'll help for the future lab reports as well. Okay, so good luck.